everyone, this is Burak Enier. We are going to start our webinar. We are here with Denis Nagy. He's a broad expert in engineering simulation and computer-aided engineering. He has 4 years experience from research and development, university teaching, and through software development. He's currently principal at BeyondCAE, a strategy and business development consulting company. Denis, I'll turn it over to you.
Thank you, Burak. I want to welcome everybody. Greetings to you all. And I can actually really say good morning at this point, because for this one, I'm sitting right next to Burak here at UberCloud headquarters in Los Altos, California. And I'm very glad to be here. So let's get started. Thank you, Brock, for the introduction. I put a slide in here if anybody wants to, when you take a look at the slides, or if you go back and download them or whatever, there's a little more detail about me here. I won't spend any time reading all that now, but I really feel I do have a unique position, having spent now over 42 years in this profession of computer-aided engineering and all aspects of it, and that I think has given me a lot of insight from various different angles about what is engineering simulation, CAE, and in particular allowing me to speculate and be given some slack in speculating on where we're going for the future here. So what I'm going to talk about today is what is MCAE today? That was a sort of a segue from the last webcast a couple of weeks ago, where I sort of brought it up to today and told how we got here, in my opinion. So again, to kind of tie those two together, I'm going to talk about a few seconds about what is MCAE today, more than just software, just what is it in total, a few key trends, key near future trend themes. In other words, what of all the things that are happening, where are they going, and what categories they fall into. I'm going to introduce what some of you are probably very familiar with, others not, is this famous V diagram that has become more and more widely used as a discussion for product development, where software plays a role in that. I'm going to talk in particular about what I feel is a dramatic potential expansion of the use of simulation. And I say potential because some things have to happen for that to be realized over any time frame, really. Okay, so I put this thing together a few years ago, which I thought was a very good way to illustrate the total solutions around MCAE, and also because I think it ended up looking kind of nice as a pinwheel or a flower. Anyway, the point here, without going through and reading again, all of this again, is that really for a mechanical computer-aided engineering solution to be there that's usable by people, there's really 4 major elements and then some overlap areas. Obviously, the simulation software tools is where it all started. And that is divided into 2 areas: working environments and computational engines. But then there's people who use it. There's different categories of those people. Up till now, generally, they can be broken into 2 groups. One are full-time simulation specialists. That's pretty much all they do at their job. And then there are product development engineers whose job it is to design, develop, and get out the door a product that will make money for their company. And they use simulation as part of their job. Then there's the whole process of what are they doing when they're using software. That's that pinwheel there on the right. And then, of course, all of this creates a bunch of data and all the issues of where is that data kept, how long is it kept, plays a role in defining a total solution. So there are really things going on in all these areas, and then each one of them overlaps so that you have training and help functions that make it easier for the people to use the software. You have simulation process management, which is a way of capturing what people do with simulation in a way that can be at least looked at by other engineers or reused, modified, and so forth. Knowledge-based engineering is really where the processes and the data together provide a basis for doing smarter and more effective simulation. And then, of course, there's simulation data management, which is how the data created by the software is actually retained. So what are the key trends in engineering simulation, in my opinion? And again, this is my opinion. I challenge or ask anybody to disagree with me, and that makes for a more lively discussion going forward from here. Obviously, development continues in the most mature branch, which is the both the GUI or environments and the actual number crunching solvers that are underneath that GUI. That area is not dead by any means, but I've always asked a question for the last 10 years or so at many different presentations. I've asked people in the audience how much of what's in the software that you've paid to license is actually used by you or any of your colleagues. And it's surprising how small that percentage is that people will venture a guess about. And there's no known answer. I just like to see what people think on that. So you're getting a lot of development in the solver and GUI area for more sophisticated nonlinear structural simulation. Of course, all of computational fluid dynamics is in essence nonlinear to start with. What you're really getting though a lot now is non-standard materials, even going beyond that into introducing materials as a design parameter when you're doing simulation, changing material laws and properties in order to see what effect that has on the product being developed. MultiPhysics, multi-fidelity, multi-scale, which are not the same thing. I'll have another slide on that in a second. But there's a lot more attention lately and going forward in those connectors in that pinwheel, because they are, in my opinion, the keys to synergy, the keys to getting the most out of engineering simulation. And so there's active work going on in all those areas, which you see listed here. And again, I won't read all this. This is just a way of capturing where those areas of ongoing work are focused. Next, as I said, there's significant growth in materials research per se, and the fact that simulation is so powerful now plays a role in even how that materials research is done. So there are people who are micro-modeling materials science ideas using MCAE really down at the micro level to determine properties of certain kinds of materials that they may want to propose to be developed. And since those materials don't yet exist, they can't be tested in a materials lab. And so they're actually doing simulated testing of new materials. And that's in areas of more exotic composites, down into the micro and nano level, so forth. Then there's multi-physics, which is different physical phenomena that interact and affect each other. And that's always the case in reality, but it's been possible for the sake of getting any kind of an answer to sort of separate those different physics phenomena and look at one or the other, whichever happens to be more important in a particular product design. But, so structural and thermal have been done together for quite a while now. Fluid structure interaction is becoming more commonly used and able to be used. Computational fluid dynamics linked with chemical reactions and combustion has been done for probably 10 to 15 years in some form, but it's getting more powerful, and a lot of development is still going on there. Then you have where you combine electromagnetics in there somewhere for products that have both structural behavior and some flow and electromagnetic fields. That is also becoming more possible, and there's more development going on with various vendors in those areas. A very key one that's much more recent is the multi-fidelity system level. In other words, the ability to look at some of these subsystems or components that have been simulated for quite a while now and say, where do they fit in the overall system that's being developed, whether that's an aircraft, a car, or whatever, and how do we actually tie those simulations at those different levels together, and how much fidelity do we need at any point in time when developing a new product? When do you have to go down into the level of looking at three-dimensional behavior of components in an automotive development, for example? So you have, in the structural area, there's always sort of been the multi-level or multi-fidelity, and that's structural software really started out, MCAE and structural, in one-dimensional material, at least bars and beams, and then went into plates and shells, and then solids. Same is true really in the flow region. You have a lot of piping network software that makes assumptions about the flow because it is a pipe and certain things are known about it. And then you get into 3D CFD, but still single phase fluids. And then you get into multi-phase fluids, which is different than multi-fidelity really, because you're just trying to take into account the interaction of different fluids. And now you have what's been going on in parallel for a long time is the sort of block diagrammatic system modeling that has been done in a lot of areas using more recently tools like MATLAB, Sabre, SysML, Modelica, LabVIEW, and so forth. They are now trying more and more to connect themselves to three-dimensional traditional MCAE because the loadings and a lot of other things that you apply in 3D traditional MCAE come from somewhere, and that quite often is from simpler representations that were done previous to that in some of these system modeling approaches. And then finally, another area which I'm not really going to talk much about, but just make you aware of the term simulation governance, or SimGov, which is the idea that as simulation gets more and more used in significant sized companies, it's viewed as an enterprise-wide resource, and it needs to be governed and administered in a way that makes it consistent, that makes sure that people are using similar tools, similar processes, and if they're not, why not? And because the company has to stand behind the role that simulation plays in developing their products when those products go out the door and get used and possibly have regulatory issues and so forth. So governance in the area of finance, it's been around for a long time in large companies, but simulation governance is now getting some more attention, leading to most likely more formalism here going forward in the future. Connection with the military view of this, people have called that simulation government sort of command and control of how simulation is used. So some of the near future trend themes, this has been a cliche for quite a while, but it's becoming more feasible in a lot of areas to actually allow simulation to drive design. And that gets to the point even of automated wrapping optimization around simulation and letting the optimization drive changes in some of the key parameters and even the shapes of products being designed. Another one, which some people have called democratization, in other words, making simulation available and usable and affordable by a much broader and larger population of engineers. Then there's, of course, the cloud, and part of the reason that I'm presenting this to you today is that this is under the umbrella or the auspices of the UberCloud, which is I'll say a few words about that later on here, but the cloud is playing a role, and everybody's trying to figure out in the near future what impact, beneficial impact, that can have on computer-aided engineering simulation. And then, of course, as I said before, the multi-scale or level, multi-fidelity, multi-physics is receiving a lot more attention in terms of presentations at conferences, being added more and more to the existing software from the vendors and leading in some cases to the development of new software that wasn't even there before. Then the mechatronics convergence, which is a way of describing the fact that in a lot of products today you get both the electronics and the mechanical behavior now interact much more in an automobile or airplane or many other products for that matter, and has to be looked at together. A lot of the requirements for how the mechanical part will behave come from electronics considerations and vice versa. And then there's the continually evolving independent software vendor ecosystems, which I touched upon 2 weeks ago. That doesn't show any signs of stopping. There will be more consolidation at the high end and more companies popping up at the low end to hopefully become the big companies of the future. And then, as I said, simulation governance will slowly receive more attention. Right now, it's just a discussion point, but I think as upper management in more companies realizes how important simulation is to their corporate behavior and their corporate well-being and future success, they will begin to step in there. I know engineers don't like being told what to do, but that's the other side of the coin, that when you get enough attention as a simulation engineer that you're going to be respected by top management, you're also going to be governed by top management. And all of these above, if you really think about it, are a mixture of business and technology trends, and that's what's going to be happening here going forward. One of the key things here is the idea, and this is starting to happen in certain industries, and certain vendors are responding to this, is doing simulation before the traditional computer-aided design or CAD. It used to be that you had to start taking some CAD geometry and going and then modifying it or doing something to it so it would be ready to use it for simulation. And so at that point, the product development engineers and the engineering organizations were sort of waiting to say, okay, we've designed all this stuff in CAD. We have some idea that it's probably going to be okay, but we really need to validate that with simulation. And so simulation as a function and the people doing it were under a lot of pressure to hurry up and validate something that was already detailed designed in a CAD system. But what was always discovered was that certain things led to redoing a lot of the CAD at that point. So the idea of using simulation to drive product development and more detailed product design features rather than following that step as verification is, although that's been an idea and is being pushed, it will continue to get pushed and it will continue to become more and more doable. And that's when simulation will not only be more mainstream, but will also upstream from traditional CAD. In other words, people always talk recently about defeaturing tools. You had to take the CAD geometry and defeature it in order to do certain types of simulation. And so that the obvious, almost sarcastic question is, if you have to defeature something, didn't you go too far? And shouldn't you really be determining those features after you've nailed down the basic design with some good simulation? A good example of that is that SpaceClaim, as a solid modeling geometry company, has targeted this pre-CAD segment and need. They partner with a lot of software vendors to be able to create and use geometry for simulation before it gets to the traditional CAD phase in the workflow of a product development company. Berlin-based Friendship Systems, which is now, is a part of Germanische Lloyd, and they merged again with Detnoris Veritas. They're a huge company in the shipbuilding and ship verification industry. Friendship Systems, who I happen to know reasonably well, wrote something recently on their website saying traditional CAD tools, the names we all know, CATIA, Siemens PLMs, NX, Pro-E, SolidWorks, although they're powerful, are detail-oriented and encompass features which may not be relevant for simulation. So it's clearly a point that a lot of us know, and now we need to do more about it. So here's the V diagram I was talking about, and this started out, software engineering thinks they invented this, but I know somebody else at SimData, Keith Meinches, who may be on this webcast, who found a reference to this, or the first use of it, way back in the 1960s in a context unrelated to software engineering. The idea that you start with customer needs and then you work your way down into refining a design and a development. The requirements cascade down to the point where when you're doing component and parts design and subsystem simulations, you have some kind of behavior that you're trying to simulate, something acting on those components and subsystems. And where does that come from? Well, it originally comes in some form from the product functions and characteristics that are determined based on customer needs. And then they start looking at how to manufacture this, and then you do some virtual prototyping, hopefully even in the downward part of the arrow, but definitely on the way back up. And then there's physical prototyping, traditional testing, on up to product validation, and then actual manufacture and bringing to market a new product. And that V diagram has become very good as a talking point for a lot of looking at where does a particular software tool or a particular idea fall in that process, or where are there gaps and needs where something is not being well done at this point. It almost, I've said that it should be a W, because what you really get is people come down that left-hand side and then they go up the right-hand side, but only in a virtual sense, meaning it's all done in the computer, and they learn a lot about rebuilding things back up to the full system simulation, because most of the requirements are system-level requirements, not subsystem or component in reality from customer needs. When you go out and buy a car, you don't come into the car dealer and say, well, I want a car where this particular piece of the carburetor looks like that and behaves like that. No, you say, I want a car that is quiet and accelerates nicely and has a good feel in corners, the various things that are all system requirements. So anyway, now it's possible to actually come down that side, go back up most of the other side virtually, and then again probably allow those discoveries and findings to come back down again for a refinement before you go up the true right-hand side of this diagram, and that would produce a W. So I've said it's actually probably more like a W now. So this is a very key point here that I wanted to spend a minute or two on, which was what a number of us feel is the dramatic potential expansion of simulation use. Now, ignore for a second what any of those numbers on the two axes mean, because that's not really important. It's just there to show something that the horizontal axis is a time axis, so those might be years beyond some point. The vertical axis has something to do with populations of engineers, but obviously not 400, probably 4 million is a better number. There are plenty of engineers out there doing product development in the world, in various industries, various types of products, and probably almost any one of them, if they're doing anything where there is a functional behavior involved, where it's not purely aesthetic, where they're not just designing something to look nice, they have to know something about how it's going to behave, and whether that's gut feel, rule of thumb, experience, or whether they could, if they had simulation and knew how to use it and could make use of it, whether they would actually do some simulation if it fit right into their workflow and process and did not slow them down. And so if you really think about it, there's a tremendous potential, and that's what this red curve shows, that going forward into the future, there's a lot of engineers who could make use of simulation in some form, and that's the key word there is in some form, because today, you have, and that's what that blue line in the bottom shows, you have people who know how to do simulation today in some form, enough that they can get some value out of it. And they use today's generation of CAE tools. And that number, you can argue that number might rise as well, but in any event, it's somewhat limited by both the capabilities in today's CAE tools, but also even much more the experience of those engineers and how they could educate or not a much larger group of engineers quickly enough to actually get that upper curve to represent reality, not just a potential. And so the real question then becomes, how do we widen the availability of simulation to true design engineers? And I mean by that functional design, not aesthetic design. And that's been called democratization by some people. I have other reasons why I don't like that word particularly, but I won't get into that here. The old paradigm was a CAD company purchases an FEA or a CFD tool or company and offers a CAD embedded version of the traditional analysis process embedded into the detailed CAD system. PTC bought RASNA, SolidWorks bought SRAC, Autodesk bought Algor, Plasotech, and Blue Ridge Numerics. Siemens PLM bought FEMAP and LMS. A guy I know pretty well who also might be on the listening in here wrote in a recent desktop engineering article that Autodesk seems to be the first company that sort of recognized that they need to do this a bit differently. And so they're doing things like Autodesk 360 and so forth that are attempting to put their arms around this issue of how to widen the availability of simulation to a much broader class of engineers. The newer paradigms are creating simulation tools, wizards, e-handbooks, things that will give non-simulation experts reliable answers to specific classes of difficult simulation-dependent problems using simulation, as I call it, under the covers, meaning if you narrow down the scope of what the simulation is supposed to be simulating, you can automate a lot more of that and hide a lot of the decisions that a simulation expert would have to make in using a generic simulation tool. Even though those tools are very powerful, it requires expertise to know how to use them. If that can be replaced by something sitting on top of those tools, such as wizards, e-handbooks, templates, and so forth, that would open up the use of the same powerful simulation, not dumbed down, simplified simulation, but the real powerful stuff that's already there, to a lot more people that wouldn't have to learn how to use it in great detail because it would have been customized for whatever it is that they're going to be doing. A lot of work is going on now in the area of intelligent templates for capturing driving and use of the right, quote, simulation at the right stage of product development. In other words, at the right positions of the V diagram. So if you take this diagram again, this chart that I showed before, the real issue is you have the current expertise requirements. In other words, what does somebody have to know to use a generic but very powerful tool today like Abacus, ANSYS, Star CCM Plus, whatever. And then you have this democratization pull. A lot more engineers saying and realizing that they would like to do simulation, they want to do it, but they clearly have no clue how to do it and how are they going to get to that point. So a lot of what's happening now and a lot of what all of us are wrapping our arms around and trying to both define and then develop is how do you close this gap? Today, what you're finding is some sporadic efforts by various software vendors. Here's an example of a sort of a wizard for doing something very narrow, you would think, for those of you on this webcast, the idea of simulating the stresses in bolts that connect two pieces of fuselage on a fighter aircraft. Sounds like a very narrow area, but there are, even within the U.S. Air Force at various engineering centers, there are dozens and dozens of people who need to do that every day. too expensive to hire that many experts to just do this some sort of repetitive simulation. So a tiny software vendor in St. Louis called ESRD happened to develop under contract to the U.S. Air Force some of these wizards that allow somebody to get those stresses in the bolts, and they don't ever know that underneath that is a finite element solver that's actually getting those results and getting them reliably and saying how accurate they are so that they can be calculated to the accuracy needed by those engineers. Autodesk also did something much more general. They created this very visual tool that allows you to basically create a truss across something like, in this case, a river, and apply certain loads to it and just immediately see how it's going to behave without knowing anything about simulation. Intelligent templates, these are ones where they have enough sophistication in them that they can be then adopted by the end users to do various types of simulation. This happened to be one for doing optics-related simulation of lenses. This was done in connection, I believe, with a company in Southern California. The Common Solutions is the company that actually develops the software to do these types of templates. And then, of course, we now have the cloud, which brings, for a lot of these engineers in that upper curve that I just showed you, the ones that want to do simulation, the cloud offers a lot of possibility here. It's clearly, like most things, it's a lot of talk or hype early on, but that turns into reality as time goes on, which is really the increasing availability of remote computing access, which has come to be called the cloud for a number of reasons. It could be the subject of a whole different presentation. I won't get into a lot of detail here. I'm actually hopefully planning to do a presentation just on the cloud related to simulation at an event here later this year. It's still way too early to predict which business models will emerge, but something's going to happen there because it's too compelling to not exploit it. There's some additional layers of difficulty, of course, in cloud-based simulation. The need to more automatically locate enough powerful computing clusters, nodes, and cores to get the job done as fast as possible, as fast as it's needed for a particular workflow. That is part of what the cloud infrastructure is working on, is the ability for an end user not to have to worry and figure out where am I going to run this, but to be able to just say, being connected to some cloud provider and saying, I just need to run this and I need whatever, I have a certain time requirement, and the infrastructure will respond by figuring out where to do that and figuring out what it might cost so they can determine whether they can afford that as well. And it will be pay as you go, meaning an end user does not have to buy an annual license of some software and install it somewhere on a cloud and then pay for an entire huge block of time on that cloud, even when they don't know whether that's going to be too much or too little. And then remote visualization, as we've seen here in the UberCloud HPC Experiment, is a big issue. The question of viewing things in the cloud versus downloading the results for local visualization. Crowdsourced practical research is what the UberCloud Experiment, HPC Experiment really is. It focuses in this area of using existing software, using existing computer hardware and infrastructure, applying that to applications, and seeing whether it can be done in a way that helps the end user move what they're doing into a cloud environment and what are all the obstacles there. I'm sure some of you have looked at enough detail at the UberCloud website to know what I'm talking about there. If you haven't, you should definitely go take a look at that. It's an open, voluntary, collaborative community. Again, I won't read all of this because this is in much greater detail on the website, but it's really meant to figure out what are all the obstacles, practical, real obstacles to making high-performance computing as a service for simulation a business reality. And as has been seen already in the various rounds of this experiment, there are a lot of roadblocks. It's not rocket science to overcome them, but they do have to be encountered, understood, and overcome. There was a poll a year ago already when this UberCloud started about what are the major challenges in high-performance computing that people are running into. And of course, intellectual property, data security is still a major concern. There's a lot of debate, and again, it could be a subject of a whole other presentation on how much of that is just worry and how much of it is real, because even security within a company's current computer infrastructure is not anywhere near as secure as most companies think it is in terms of being hacked and so forth. So a lot of the risk of having something out there on the cloud is maybe more perception than reality, but it's still, even if it's perception, it has to be dealt with. And then there are the other issues, as you see there in that poll, and those colored bars are, and the percentages are how many people responded saying that those were their major challenges. The HPC experiment started now about a year and a half ago. There are probably even more than 900 by now. It grows daily here of companies that sign up. It tells me I've just used up all my time here, but I'm almost done. Okay. There are participants from at least 48 different companies. The fifth round of this experiment just started on February 1st of this month with 25 to 30 new teams. Teams get numbered consecutively in each round, and there have been somewhere around 140, 150 teams now in total. And new teams get created, or teams get carried forward if they didn't finish in a previous round, and they get a new number. You can take a look at any of these websites, and when you download these slides, even the PDF form, these are all hyperlinks, so you can just click on them and actually take a look and sign up if you're not already a registered participant. And you can even be an observer as a participant, but it's much more interesting when you get involved in some way, whether you're an end user, a software vendor, a hardware resource provider, or just somebody who knows enough about this issue to want to participate, being part of a team. Let's go up here. There we go. This is just one of the teams that was very successful, and you see there that ANSYS was involved as the software. Science and Computing was the infrastructure provider with Extreme Factory, and this was a CFD application, drying of moist particles with hot gas. So you see what's being done is not Mickey Mouse simple simulation either. It's fairly realistic and fairly complicated. If you want to look at all those teams, the most successful ones basically for the first two rounds of this experiment, there is a compendium which you can go on the website and click on the link and you just sign up to receive the PDF version of this, sponsored by Intel. There will be another one coming out fairly soon, which covers the best teams in the rounds 3 and 4. So the broader MCAE environments, just the last remark or two here. For decades, there's been this ongoing debate of integrated from a single supplier versus best of breed from multiple vendors. I remember presenting things about that back in the 90s, and people trying to claim to be a single supplier that could do it all back in the 80s already. Every time anybody tries to do that with a closed system, they fail. They have to end up opening up that system, because even today, the tools that people really should be using come from a number of vendors, and you have to have a way, even if the environment that you're using them in is somehow integrated from a single supplier, you have to be able to use tools from many different suppliers in your processes and your workflows. So you want seamless integration, but of the best of breed, not from a single supplier. Vendors of solver tools and environments have focused and oriented mainly around their own tools in the past, but they're opening up to heterogeneous tools needed that will remain for the foreseeable future, this trend. And those that have responded more rapidly to that are actually well positioned to take advantage of that. One company that comes to my mind always, probably because they never did have traditionally a good number crunching solver, they focused on this open environment is Altair with HyperWorks. But they're not the only ones whose environments are now relatively open. So if you look at this idea of best of breed vendors in the main MCAE application areas, you have flexible mechanics, multi-body dynamics as an area, fluid thermal solvers, electromagnetic solvers, CAE GUI environments, and generic meshers and viewers to be used with solvers. And then you have simulation lifecycle management, and these are some of the players. Those are not exhaustive or complete lists, but the thing to point out here was that if you take a look, for example, where ANSYS shows up, you get the fact that ANSYS seems to be closer to this idea of being both best of breed and integrated, at least at the large level of being able to use tools in these different areas from one vendor, which is why ANSYS is the largest current MCAE or even CAE company, as I showed in the presentation 2 weeks ago. I did point out this idea of work is going on, and software is being extended in all these different levels. Multi-fidelity and multi-physics have been, I guess, more traditional areas of expansion and development, but the multi-level, going downward from viewing materials as a continuum down to nano layers where you have molecular and even atomistic representation of the simulation you're trying to do, and then going up from the traditional 3D to subsystems and systems, and then systems of systems, which really begs questions of what is that even. Siemens did a good pictorial representation where they took the V diagram and showed that it actually has plays a role in all those different areas: mechanical, electrical, electronics, which is different than electrical, and then in software engineering, and how all those V diagrams are used by people doing product development, focusing on those different areas, but they all also involve collaboration in any end product that has everything in it, that has mechanical, electrical, electronics, and software parts to the product. This is just one simple example of what I call the mechatronics conversion, where in developing a backhoe excavation machine, you've got hydraulic circuits and the need to simulate those with some sort of hydraulic block diagram software. You have load sensing circuits, which is pure electronics, deformable mechanical components, which can be done in some sense by simplifying, but then when you get to the actual soil model that is needed, that's really full 3D. And you have the physical side, and then you have the logical or topological side of the simulation. Logical is misleading because then people think of logic circuits. This is not meant in that sense here. NAFEMS, which is a traditional association related to MCAE, and INCOSE, which has been in existence for a couple of decades as the International Council on System Engineering, have gotten together recently to recognize the fact that this mechatronics conversion and the push towards model-based systems engineering is going to require a lot more interaction between the traditional types of engineers in these two areas. And so they formed a formal partnership, and they formed a joint working group. Each organization functions a lot on volunteer working groups, but now they have one that has members from both organizations called the System Modeling and Simulation Working Group. It was started in mid-2012. If you are a member of either of those organizations, take a look at what they're doing, and if you're interested, get involved. So this is really in a mechatronics diagrammatic sense how INCOSE is coming at it from one side, NAFEMS from the other, and they have formed this organization, this working group. So with that, I'd like to end my presentation. Thank you all for those of you that didn't log off somewhere in the middle. Thank you very much. As we've said, you can get both these slides with the hyperlinks in them from either the UberCloud site, or you can email me directly and get them from me. If you have any questions or comments, please feel free to send me an email with them as well. And with that, I'll turn it back to Barack.